Hello everyone, how are you? I'm Namuddin Ahmad here, and today we are going to talk about real numbers. So let's get into it. To understand real numbers, we'll first go through what are natural numbers. Okay. These are the classifications of real numbers. So let's see the natural numbers first. Okay. So natural numbers are basically what we know as numbers, like 1, 2, 3, 4. These are natural numbers, right? So these are basically the natural numbers. So it has the positive whole numbers like these, which are either prime or composite numbers. By prime, what we mean is that numbers that are only divisible by those number and 1. So if you see these three numbers, you'll see that they're divisible by them, or they're divisible by 1. Composite numbers means numbers that are divisible, that has multiple factors. For example, if we take 4, we can divide it by 1, we'll get 4. If we take 4 and we divide it by 2, we get 2. If we take 4 and divide it by 4, we get 1. So these type of numbers like 4, 6, 8, these are composite numbers. Okay, and then there is integers. So integers are all positive and negative fractionless numbers. So basically, previously what we said for natural numbers are all the positive whole numbers, right? So there were 1, 2, 3. Integers consist of negative numbers as well, so it will consist of -3, -2, -1, 0, 1, 2, 3. So these are integers, right? These are integers. Now here they included the fractionless number because you'll see that there is no fraction. That is, this is not an integer. This is not an integer, so that's why they included the fractionless number in the definition. Now, and the next one is the fraction number, right? So what is a fraction number? So fraction number, that is a number that is not a whole number, right? So for example, 3 by 2, what we wrote before, 3 by 2, this is a fraction number, so we can't express it in a whole number or in an integer number. So here they used p by q to define a fraction number where q won't be equal to 0 or it won't be equal to 1, and p won't be divisible by q. So if I write a number, say 5 by 3, where 5 is p, right, and 3 is q, then according to this definition, q won't be equal to 0. That is, you see that 3 is not equal to 0, it won't be equal to 1. So 3 is not equal to 1. And also you'll see that p in this case is not divisible by q. So here you can see that 5 is not divisible by 3. So since it's not divisible, we have to represent it like this, in a fraction way, right? In a fraction. So that's why it's called a fractional number. This can also be negative here you can see this can also be negative, right? This can also be negative, so it can be even minus 5 by 2. It can be minus 5 by 2. But these are some simple fractional numbers. Next we have rational numbers. Okay, so what are rational numbers? Rational numbers are numbers that you can represent by p by q, where q won't be equal to 0, but q can be equal to 1. So say it can be like 3 by 1, right? So 3 by 1 would be equal to 1, right? But it can also be say 11 by 2, so that would mean 5.5. So these are rational numbers, right? So here what that says, two mutual prime numbers. Any rational numbers can be expressed as ratio of two mutually prime numbers. So in the first example is 3 and 1. So these are mutual prime numbers, that is they don't have anything in common within them other than 1. Here 11 and 2 are mutual prime numbers because they don't have anything in common within them other than 1. That is, they don't have GCF. There's the greatest common factor is 1 itself. So here is that you can see that all integers and fractions are rational numbers. Okay, so irrational numbers are numbers that are not rational. So here if a number cannot be expressed in the form p by q, where p and q are integers and q is not equal to 0, that is called an irrational number. So what do we get from that? What does it mean? So say if I write a number, say root 2, right? If I write a number root 2, then I can't express it like this. You can't express root 2 in this form, right? So when this type of cases occurs, we call this an irrational number. Okay, irrational number. So another thing is that you can't show it in the p by q form, and also you can't show it in the p by q form where the p and q are integers and q is not equal to 0. Here there are some other examples, like root 3 is also another example, which is equal to 1.732. So you can't put it in p by q form where p and q are integers. So this is an irrational number, right? So point made here is that no irrational number can be expressed as a ratio of two integers. No irrational numbers can be expressed as ratio of two integers. So decimal fractional number. So what is a decimal fractional number? So when rational and irrational numbers are expressed using decimal sign, they are called decimal fraction number. For example, if I say 3, right? So I can just write it like this, or I could write it like 3.0. So this is a rational number, and I'm expressing a decimal form. So this is a decimal fractional number. The other forms, say such as 5 by 2, this is a rational number, right? This is a rational number. I can write it like this, or I can also write it like this, 2.5. So this is basically the same thing, but and when I'm writing it like this, it's called a decimal fraction number. So for irrational numbers, say for example root 3, we have 1.732, right? We have 1.732. So this is expressed in the decimal form. This is a decimal fractional number. So here there's something to mark out. If there are finite numbers with digit after decimal sign, then this is called finite decimal fraction. And if there are infinitely many digit, then it is called infinite decimal fractions. For example, 0.52, here we have a finite number of digits after the decimal point, so this is finite decimal fraction. But say if I write 4 by 3, then if you press it in the calculator, you'll get 1.33 and blah 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 blah, it goes and on and on. So this is called an infinite decimal fraction. Okay. So in terms of infinite decimal fraction, there are two types. There are one that repeats, like the digits after the decimal point, it repeats, and then there are those that doesn't repeat. For example, this one here, you can see that 3 repeats again and again. So these are called infinite repeated decimal fractions. But for example, if we write root over 5, right, so it becomes like 2.1 2 3 5 1 2 3 6 7 and on and on. So he said these numbers are not repeating, like after the decimal, the numbers that come, they don't repeat, right? They don't repeat, like here, like 3 is repeating, they don't repeat. So this is called infinite decimal numbers without repetition, right? So here are some other examples. You can see the 122 divided by 99. This does not this repeats, and there's some other examples here. So that's for the decimal fractional numbers. So now, what are then the real numbers? So all rational and irrational numbers are called real numbers. For example, if I write 0, right, that's a real number. If I write -1, that's a real number. If I write +1, that's a real number. If I write -half, that's a real number. If I write +half, that's a real number. So these were numbers that were rational, right? Numbers that in the p by q form. If there are numbers which I cannot represent in the p by q form, like the irrational numbers, like √2, right? These are also real numbers. So all the rational and irrational numbers are called real numbers. So these are real numbers, right? All of the rational and irrational numbers are called real numbers. So there are positive numbers, there are negative numbers, there are non-negative numbers. So any numbers that are higher than 0, any number that are higher than, regardless if they're fractional number or they're integers or they're irrational, they're greater than 0, then these are positive numbers, right? Okay, if they are not greater than 0, they are smaller than 0, then these are called negative numbers, like √2, -2, -half, right? -2, -half, -√2. These are these negative numbers. So what are non-negative numbers? Non-negative numbers are all positive numbers including 0. All positive numbers. And so if we draw like say a line diagram, a number diagram, right? So this is say a number diagram. This is 0, right? Say this is 0. This is -1, -2. Say this is -1.51, 2. So this is sorry, it's not minus. This is say 1.5, right? So when we're doing it like this, right? So we're doing it like this, then sorry, where is it? Also, all the positive numbers including, so these numbers, these positive numbers including zero. These are called non-negative numbers, right? These are called non-negative numbers. So now we'll see a chart. So this is a chart that completely highlights classifications. First we have on top, we have the real number, right? We have the real numbers, then we go rational, okay, we go right rational numbers, and then we get irrational numbers, right? So from rational we have integers, and fraction, right? We have fractions. So from integer with fraction, so from integers there's positive, there's zero, there's negative, right? So there's three kinds. From integer we got positive, you get zero, we get minus, which is negative. And from fraction there's simple, right? There's decimal, there's the decimal. So from positive there are prime, 1, and non-prime. So within the positive we have prime, say we have prime, like 5 is a prime number, so we have 0, and then we have non-prime, so those that are not prime, those are composite, right? So by non-prime it means that it's a composite. Okay, now from simple there are proper and improper. Those are other different types, so you can just check it on the text in these books, which you can find in Bangladesh government's website. There's NCTB's website. You can find the definition. It's not that really important. There's proper, improper. Now in the decimal there are finite and infinite repeated, and there's also mixed kind. And from the irrational there is infinite decimal without repetition. So infinite decimal without repetition. So these are like all the classifications that you would need. Okay, let's look at an example first. Here you can see that in the first example they have asked us to find an irrational number between root 3 and 4. Okay, to find roots, we know that root over 4 is equal to 2 and root over 1 is equal to 1. So when we are asked to find any numbers, root of any whole number is in 1 and 4, that is 2 and 3, it'll end up as say 1 point something. So here root 3 is equal to 1.73205008. And how they did it is that they first took two numbers, say a and b, both being rational and they being between root 3 and 4, where a is equal to root 3 plus 1 and b. If you just look at this example you'll get it. It's not really that much important in terms of what we are trying to achieve here. Okay, let's look at over here. Okay, so if you are interested, if you need to clear up some basic, here are some basic characteristics of addition and multiplication. Basic characteristics of addition and multiplication process of real numbers. So if you can check it out from here, right? It's given all of it. You can just check it out there. 5, 6, 7, 8, 9. So if you don't understand any of them, let me know in the comment section. Now here they have they have provided a proof of proposition, which is very common for students of high school. Here you can see that root 2. The proposition was, is root 2 an irrational number? Is root 2 an irrational number? And they have provided the proof. This is not important now for our goal, so you can just look at this to enhance your clarification. Okay, now we're going to look at example 2. In here we have been asked to prove that when 1 is added to the product of 4 consecutive natural numbers, this becomes a perfect square. Suppose 4 consecutive integers are x plus 1, x plus 2, x plus 3, right? So the first one is x, then we add 1, then we get x plus 1, then we add 2, which is the one after x plus 1, and then we add 3, which is the one after x plus 3. So that's how we're going to do it. So if we add 1 to the product of these 4 integers, right? So this is the product of these 4 integers, and then we add 1 to it. So what does it become? You can see from the multiplication steps here, at first we take these two, and we get x squared plus 3x, and then we multiply these two, we get x squared plus 3x plus 2, and 1 is then kept separated. So we then assume x squared plus 3x, which is common in both of these, as a. So we get a into a plus 2. 2 comes from here, so it's a into a plus 2 plus 1. Then we multiply this a into a plus 2, we get a squared plus 3 plus 1. This is then written as a plus 1 whole square as per the theory. As per the theory, a squared plus 2 into a into b plus b squared is equal to a plus b whole square, right? So here b is actually 1. B is 1, and this is, you can say, 2 into this here, 2 into a into 1, and b as 1, so this becomes a plus 1 whole square, which is here. So then we put the value of a, which is x squared plus 3x, we get 3 plus x squared plus 3x plus 1 whole square, and this entire thing is actually represented as a whole square, right? In parentheses, which have a square on it, so this is a whole square. So what we can write from this is that when 1 is added to the product, of any 4 consecutive natural numbers, this then becomes a perfect square. So that is proved. Next is decimal fractions. I think we talked about this, that we can represent any real number in decimal fraction. Basically, the 3 types they're talking about. 3 types is finite, 3 types it's finite, repeated, and infinite. Repeated or infinite. Okay. So basically, there are these 3 types they're talking about over here. Again, they have defined those finite decimal fraction, repeated, and infinite decimal. I think we reviewed this, and here's a remark which says that finite and repeating decimal fractions are rational numbers, whereas infinite decimal fractions, so we talked about this also, values of any irrational numbers can be determined up to any desired decimal place if numerator and denominator of a fraction can be represented by a natural number, then the fraction is a rational number. Okay, so here there is a work given. They asked to classify the following numbers with reasons, like if they're like rational, irrational, or like the repeated decimals, that sort. So here is a thing. Here is a process of writing a repeated decimal. If you say a number is given 23 by 6, that's going to end up as 3.833, right? So this is a repeated number. So it's just normal divisions, and you'll figure it out. So is the part of the repeating decimal fraction. So this part which repeats, right? 33 is repeating the part of the decimal fraction. So this part which repeats the 33. Here what they're saying is that the part of the repeating decimal fractions that appears over and over again is called repeating. So it is called repeating. So the remaining part which does not repeat is called non-repeating. Okay. So in a decimal number, if every single digit after decimal point is repeating, then it is called a pure repeating fraction. Otherwise, that fraction is called a mix. For example, you'll see that 1.3 is a pure repeating fraction if we like repeated fraction, or sometimes written like this. There's this cap that's put on top of the repeating decimal, right? So these numbers are called pure repeating. These are pure repeating fractions, whereas a number, say for example 4.235112, right, here only the 2 would repeat and the numbers that come before it won't be repeating. So this is not a pure repeating fraction. This is a mixed repeating fraction, right? So that's what they're saying over here. And then there's another example where they're expressing 3 by 11 and 95 by 37 into decimal fraction. These are just normal divisions we go through. So if you use the calculator, you'll get these results. It's not a problem. We're just trying to familiarize ourselves with the terminologies. Here in example 4, okay, here they're showing how to convert repeating decimal fractions into common fractions. So repeating decimal fractions, right? These are repeating decimal fractions. Say this one, and these are repeating decimal fractions. How to convert it into common fractions? So first, they're going to write it like this. So first, say we write 0.3 into, we just break it as it is, right? So then we're going to multiply 10 with this. Multiply 10, and by multiplying 10, we mean that we write this, and into 10. So this is going to become like this. So why 10, right? So I think then they're multiplying it with 1, and then what this means is that this into 1, right? So this becomes like this. So why multiply it with 10 and 1? So in this number that they're trying to convert this 0.3 repeated decimal that they're going to convert. You'll see that after a decimal there's only one digit. And that's the digit that's repeating, right? So that's a repeating. There's no mixed digit over here. So since there's only one digit, there's going to be 1 and then a 0 after it, which makes it 10, right? There's 1 and there's a 0 after it, which makes it 10. So that's why they're going to multiply it with 10. They're multiplying it with 10. In the next number, if you notice that it's 0.24, right? It's 0.24. There are two repeating decimal digits. The 2 digits after the decimal that's repeating. So in this case, they're going to multiply it with 100. They're going to multiply it with 100. See, there's multiplying it with 100, right? And afterwards, they're going to multiply it with 1. They're going to multiply it with 1, and then, you know, here what they done, the first multiply, they just expand the number. They first expand the number, then they multiply it with 10, and then they multiply it with 1. So they subtract the product of 10 from the product of 1, and they get a result, and then they express this result as the conversion, because when they're subtracting, they take 0.3 as common, and that leaves us 10 minus 1, which is 9, and then divide 9 from the result of the subtraction, and it becomes 1 by 3. Okay, so here in 0.24, it's the same thing. It's the same thing. So multiplied with 100 and 1, and they take 0.24 as common, and that's left with 100 minus 1, which is 99. And here what they have is actually 24, because 24.24 minus 0.24 is 24. And they just they divide 24 by 99, and this is what they get is 8 by 33. Okay, so the next number is 42 point. So the next number is 42.3478, right? Where the 7, 8 are repeating and 3, 4 are mixed. Notice here that after the decimal there's 4 digits, right? So they're multiplying it with 10,000. They're multiplying it with they're multiplying it with 10,000 the first time, and the next time they're multiplying it with 100. So why 100? Because there are 2 digits. If you notice that there are 2 digits that are not repeating, right? Here you can see that there are 2 digits that are not repeating. So for this reason, they're multiplying it with 100. The next time they're multiplying it with 100. So they're going to take that common, and we get 9,900. And here, after subtraction, they get this, and it's the same process. It's the same process if you look at it. And that's how it becomes. There's an explanation of the process. If you look into it, you should look into it. And then if you come up with any questions in mind, then please leave it in the comment sections. Same thing, another example for conversion. Okay, here in example 6, they convert 45 45.2346 into a common fraction, right? So here what they say, this is actually the rule for converting repeating decimal fraction into common fraction. In the previous one, converting repeating decimal fraction into common fractions. So this is another method. This is actually another method, right? Instead of multiplication, they're going to go into direct. So here you can see that they subtracted 452, which didn't have any cap in the entire number. So they're going to subtract 452 from this entire number. So this is the entire number. They're going to subtract 452 because 452 did not have any cap, and they're going to divide it by 9990. Okay, so why 9990? So if you look into this part, right? This part there, if you take this as 1, so this is 1, say take this decimal point as 1, and then all of the rest of the digit that comes after 1, you count them as zeros, right? So you get 10,000, and then you subtract just 10 from it, because there's decimal again, and there's only one digit after that is not repeating. So you just write down 1 for the decimal and a 0 for that, so you get 9,000, and sorry, you get 9,990. So divided with 9,990, and then it's very regular. Here there's an explanation. So 2 for 2 is 0, and for this 3 is 999. So this is another way of converting repeating decimal fractions into common fractions. Okay, here are a bit of definition discussion. Similar and dissimilar repeating decimal fraction. So what they're saying is that if for 2 or more repeating decimal fraction number of digits, if for both 2 or more repeating decimal fractions number of digits both in repeating and non-repeating parts are the same, and they are called similar repeating decimal fractions. Otherwise they're called dissimilar repeating decimal fractions. For example, here similar repeating decimal fractions, but if for 2 or more decimal fractions, here if we expand, say 12.1245, right, what we get 1245. So what they're saying, this is similar repeating decimal fractions, like 2 or more repeating decimal fractions number of digits. Okay, 2 or more, if 2 or more repeating decimal fractions, and for this case say 0.3456 here, you'll see that it's a bit different, right? It's 4, 5, 6, 4, 5. These are called dissimilar repeating fractions. Okay. Okay. Excuse me. Okay, here's a bit of a correction. So what are the similar and dissimilar repeating decimal fractions, right? Okay, between, say if I write 12.45 and 6.32, which are both repeating decimal fraction, you'll see the number of non-repeating is 0 and the number of repeating part is 2. So this is similar repeating decimal fraction. But if I write say 0.345, so this is the repeating part, and 7.45789, right? So here you'll see that there are 2 non-repeating, but there's only 1 non-repeating, so, and also there's 3 repeating. That's repeating, since the repeating non-repeating part is not equal, so these 2 are dissimilar repeating decimal fraction. Now what we're going to do is we're going to convert dissimilar repeating decimal fractions into similar ones. So to do that, okay, let's say here is a conversion, right? So look at this conversion. So this is 6.4537, right? So we first convert this. Oh wait, I think this is not an example. Oh sorry, this is not an example. This is an example 8. Say example 8. So here we're asked to convert 5.6 repeated, 7.345 repeated, and A is 10.78420420 repeating decimal fractions. Now, here's a note that how to do it is that between 5.67.345 and 10.78423 in repeating decimal fractions have respectively 1, 2, and 3 digits in the repeating part. So they have 3 digits. Here 1, 2, 3, and 3 repeating LCM of that is lowest common multiple. So LCM stands for lowest common multiple. So what is lowest common multiple? So if I write 6, I can write it in 2 into 3. Here I can write it in straight 3. If I write 4, I can write in 2 into 2. So the lowest common multiple would be I think 2 in this case. Now you can take 0. Lowest common multiples would be 2 into 3 between these two, right? So the lowest common multiple would be 2 into 3. Okay, sorry for distractions. So that would be equal to 6. So this is what's the lowest common multiples. Now we get 2, which is a common, and also we'll take 3. Since it stands out. Okay. So here between 1 to 3. Between 1 to 3. Between 1 to 3. So LCM of 1 to 3 is 6. LCM of 1 to 3 is 6. So in order to convert into similar repeating decimal fractions, we must have 6 digits in the repeating part of every number. So for 5.6, we'll just expand the repeating 6 to 6 numbers. For 7.345, where 45 is repeating, we'll expand the 45 into 6 digits. And for again the next number, we'll expand the repeating part into 6 digits. Now desired similar repeating decimal fractions are respectively these numbers. So that's how you convert it. So what you do is figure out the number of digits in the repeated parts of each and every number, then you take out the LCM of those numbers, and then you make sure that the repeated parts are in all the numbers are equal to that count in the LCM. So here's another note, or also here's a work. So again, you just use the LCM. From the repeated parts. You can see there are no repeated parts in the first one. There are 3 and there's 2 repeated parts. So since there's no repeated parts, so you do the LCM for this one and you make sure the repeated parts are sized up likewise. And if you struggle to solve it, you can leave a comment, and we'll see into it later on. So here's a way to add, how to add repeated decimal fractions. First they expanded it. The way that the expansion worked out is, okay, they were dissimilar repeated decimal fractions. So what they did is, first they make sure they were similar repeated decimal fractions, the numbers equals, and they started the addition. Here you'll notice here in the bracket, but they've written 8 plus 8 plus 7 plus 2, which is equal to 25. Here 2 is in hand. What's going on over here is that they have taken 6. the LCM of the repeated numbers is 6, right? The LCM of repeated number is 6. So when they have reached the 6th digit from the right to, while doing the addition, 6th digit, how they did it is that they added a 2. They took 8 plus 8 plus 7, plus they added a 2 with it, which was, I believe, in hand, so that result 25, and then they keep the 5 and took 2 in hand. Here 2 of 25 has been added. So while doing the normal addition, this is the result. This is the result of the normal addition. This is the result of the normal addition after converting the dissimilar decimal fractions to similar decimal fraction, normal result. But when they reached the 6th digit, as LCM was 6, the number that was in hand was added later under the last digit, so, and doing this, the result that came is the actual result, so the result is this, not this. Okay, remember, this is very important. This is not the result. Okay, this is not the result. This is not the result. This is the result. It's very important to understand where this 2 come from. LCM is 6. LCM is 6 from the 6th digit. The 6th digit from the right while doing the addition. The number that is carried is then added over here. Same goes right here. Here they are. Okay, here they have used another method to simplify it. So in order to clarify addition at the rightmost digit, we have solved the addition the different way. Okay, what they have done it is that when they expanded as per the LCM count, after the expansion they have kept the last 2 digits separated. This is 89, the last 2 digits, they've written 89 over here. The last is 87, they have written 87 over here. The last 2 digit is pardon, no, it's not the last 2 digit, is the let me see, here after the end of repeating part, some more digits have been taken. Oh, sorry, so it's not the last 2 digits. If this were written, even after the 6th digit, it would come as 89. If this was written after the 6th digit, it would come as 87. If this was written after the 6th digit, it would come as 79, not as 98. That's how they've written it here after the end of repeating part. Some more digits have been taken. So that's how they have actually sorted this out. Just 1 second. Okay. The next example is also carried out like that. So they want us to add 2 dissimilar digits, similar decimal fractions. So they break it to similar decimal fractions, and here you can see where this one doesn't have any repeating part, so they just added 0 and put cap on it to make it like a repeating part. They added 2 more digits after the 6th digit, because 6 was the LCM of these numbers, and then this is done as the first method. Okay, here's a note. Okay, here's in the following is explain why 1 is subtracted from the rightmost digit in different way. So that was addition. This is subtraction. So for subtraction, we can also use a shortcut method. We just have to keep on writing even after the LCM count, and then we just do the subtraction, we get the desired result. Otherwise you have to do this, right? You have to subtract normally, then you get a result. Okay, you subtract normally, then you get a result, but that's not the real result. So you have to subtract another number which you have to figure out from the 6th digit from the right, and then that is 1 here, which is carried. Then we have to subtract that 1 and get the real result. So this is the real result. But you can also do it how they have done it over here. Okay, how they have done it over here. Okay. Here is a multiplication that has been there is a multiplication, so we're asked to multiply 1.326, I think. So when you have to do this, you have to simplify. So how it's done again, you know, we looked into it, this, it's not much difficult. So it's 113, so entire number without decimals, without the cap, minus 11. 11 is because there's 1 and 1, and then it's divided by 9 because there's only one non-repeating number and one repeating number. So you looked through this, you just go through it and you get it over here, right? Sorry, 11 is because 1 and 1 is not repeating. There's a repeating cap over here, so that's 11. And here's 90 because of this only 1 repeating and 1 non-repeating after the decimal. Okay. We go on and go on. That's pretty much it, I think, for the basics of this chapter. Okay, the basics. There's a lot of exercise out there if you want to complete the exercises. You may do them at your home. If you have any problems, let me know in the comment sections. I'll get back to you at my convenience. So this is chapter 2. Okay. No, I think it's the first chapter. It's not chapter 2. I think this is the first chapter. Yeah, this is chapter 1. So this is chapter 1 from this downloaded from the website of NCTB. It's the English version book for class 9 to 10. English version math book for class 9 to 10. So if you're interested, you can go to the website and search and find it. It's very simple, very easy. Thank you.